Okay, welcome back to Machine Learning for Structured Data. Today we're going to be talking about the continuation of what we had begun last time, which is sequence-to-sequence models. So last time we kind of looked at just standard recurrent neural networks, and we had focused specifically on element networks. But we're going to go beyond that to sequence-to-sequence models. And then, we might kind of just get started on Bayes nets. Okay. So, one question you might have is, what did the results of that survey you took look like? Okay, so responses are still coming in, but there was actually enough of you had responded by the time I was putting that figure together, I think 39 of you at that point, that already this clear trend had emerged. So you can disregard these actual percentages. They aren't meaningful. What matters is that 30 out of 39 people have seen hidden Markov models before. Okay, so what that means is I don't really want to spend a lot of time on a topic that 75% of you have already seen. So but I think it's actually still important material. So I'm going to come up with some way, either like a video lecture or a recitation or something that kind of creates an optional way for you to see this picture of hidden Markov models if you haven't before. But then we'll kind of talk, so maybe half of you, about 24 out of 39, have seen Bayes nets. We'll talk sort of about Bayes nets, but we'll move quickly so that we can get to kind of the new stuff like conditional random fields. Okay, so that's sort of the plan. We need to talk about these things because we want to be able to draw connections to them. We want to be able to tie everything together into a cohesive framework, but we can be somewhat flexible in terms of how we use your time in class. Okay, so any other questions? From last time, learning to search, RNN. Okay, so one good question that came up after class was kind of pushing me on this, what is the difference between imitation learning and reinforcement learning? I still don't get it. Okay, so again, according to the survey, only like half of you have actually seen reinforcement learning. That's fine. I just still want to kind of make this point. So there are lots of differences, but they all stem from one fundamental difference. Imitation learning assumes that it has access to an oracle policy, pi star. Reinforcement learning does not. Because of that assumption, they go in very different directions as subfields. So, for example, one of these contrasts that I thought was particularly interesting that we painted in office hours was between Q-learning and Dagger, where we said, both have some notion of exploration and exploitation. Okay, this is a very loose analogy, but you could say Q-learning, if you know it, it does exploration in a random way. It has a random policy. So it explores the space of possible actions using that completely random policy. And then it does exploitation by relying on what it has learned so far, its model's policy. By contrast, Dagger is also doing exploration and exploitation, but the exploration happens more through the model's policy. And the exploitation happens through following the oracle. So I don't think that the imitation learning literature would use this exploration, exploitation terminology to actually refer to what it's doing, but I think the actual connection is kind of interesting just to see it. Okay, so this is the same slide as before with just the release date and deadline pushed back by 2 days. We're still within our plus or minus 2 days of releasing. We'll see whether we need any additional plus or minus there. It's never minus, it's always just plus, let's be honest. We never release early. Okay, especially not on a new class. Okay, so let's talk seek-to-seek. So we went through, why are we talking about seek-to-seek? It's just this powerful framework that allows us to capture all of these different tasks. And so far, we just kind of got through part of recurrent neural nets. And I wanted to pick up at the point of LSTMs. So LSTMs, or long short-term memory models, are motivated by the fact that LM networks, or standard recurrent neural networks, have trouble learning long-distance dependencies. Okay, so this is extremely disappointing because the whole point of using an RNN is to learn long-distance dependencies. That's what we wanted. We said we wanted to get out of sort of this standard feature world where we can only go back, say, a fixed window of words, and we want to move to something where we can get arbitrary long-distance dependencies. And so LSTMs try to combat this issue. And so one of the things that is particularly problematic in RNNs is the vanishing gradient problem. And so what we're looking at is actually a figure that shows the sensitivity of the gradient to the input at time t equals 1. And so what you can see here is that the actual value of the input at time t equals 1 is going to have less and less effect as the time steps go on. So what does this mean? Well, if you want a long distance dependency, that's kind of like saying, the first word in the sentence was critically important. Say you're doing translation, and the first word in the sentence is critically important to getting this translation right. It's something like, it's the word no. Without it, the entire translation goes wrong. Like, I like this food. Okay. No. Wait, no always works. So can someone correct my example here? Okay, we need some sort of modality on the verb, right? I want to like this food. No, I want to like this food. So no here is like the critical word that's telling you which direction things are going. And so as we have this critical word feeding in, we see that gradually as the sort of node becomes less and less shaded, the effect of that word is having less and less of an impact on future units in the network, okay? So what an LSTM does is it basically just has these little gates that can allow information to flow through a lot more directly or to get stopped completely, right? So if that really important word, now we're all going to remember this example of no, I like this food. It's going to be this great example of RNNs that doesn't make any sense at all. Okay, so if you imagine that word no being fed in, and at every time step, instead of being passed through, let's actually jump back here to our definition of an LM network, since we haven't seen it for a couple days here. So what we want here is our definition of the recurrent net. And so you'll see that HT is defined as some matrix times XT, some matrix times HT minus 1 plus some bias term or intercept term. And it's passed through some nonlinear function, here calligraphic H. So let's suppose that calligraphic H is something like a sigmoid. Okay? And so what's going to happen is that calligraphic H, that nonlinear function, is going to be sort of squashing down the influence of whatever is going through it. Okay? And so that's exactly why we end up in a situation like this. The impact of that unit is just getting squashed more and more every time it goes through that sigmoid. Okay, so how can we fix this? Well, the LSTM is going to say, sometimes it's going to pass through the nonlinearity, but sometimes it's going to go through this gate that lets it just sort of sail right on through. And so you can see pictorially what's going on here is there's these little circles and these little lines. And these are sort of supposed to indicate whether or not a gate is open or closed. Okay, and so here we have an open gate, and an open gate, and an open gate, and an open gate. And so the information from the input at time 1 is just getting shuttled along down the line. But these gates, which would be accepting the input at time 2, 3, 4, 5, and 6, those are actually closed, and so they're not getting let through. So the information is able to propagate really well, and it's not distracted by the other words in the sentence. Okay. At this point, it gets to time step 6, and there's an open gate on the top that allows that information to flow out the top. Okay, this actually already also happened at time step 4 as well. But then finally we hit this closed gate, and the information from time step 1 doesn't continue to flow through. Okay. So this notion of gating is used all over deep learning. It's become sort of prominent within individual cells of, say, a recurrent neural network. LSTMs are just one example of this. I'm not going to talk about GRUs, but they're another popular one. It's also been used to sort of capture the ability to pass information through different levels. So if we have, we'll look in a second at a multi-layer LSTM, and we can also have this sort of skipping of information that can allow it to pass through in different levels of the LSTM as well. Okay. So here we can kind of draw a picture of an RNN with LSTM cells, and it looks just like before, but now there's just sort of some additional complexity captured within each of those cells, right? So the actual hidden information at time step 2 is still a function of x2 and the information at the previous time step. But we have some additional mechanics in there, these gates, that are actually allowing it to flow through in a slightly different way. Okay, so so this is an actual depiction of one of those cells, and so here you can now actually see explicitly the different gates that we had mentioned. So there's an input gate, a forget gate, and an output gate, and so these are corresponding to the input, the forget gate, and the output gate, I sub t, f sub t, o sub t. And the gates themselves are actually going to control the information flow through this cell. Okay, so as well, we have this sort of new term, CT, and CT is sort of the part of this whole thing that that we need to be a little bit careful of to make sure that our picture actually reflects sort of what's going on here. So CT is sort of an additional vector within this cell, in addition to what we usually think of as its output, which is HT. And CT is going to store essentially some mixture of the input and forget gates, right? So you can actually see that happening here, right? Where it's using both the input and the forget gates. And what that means is that the input gate is actually just affecting sort of this part of the equation that it looks identical to the LM network that we had before. Okay. So you could think of this as essentially putting some weight on how much we want to take from the previous sort of standard setup of the LM network, And the forget gate is what's taking directly from the previous cell. And so the extent to which, oh, and sorry, if this might not be obvious. So the input gate is a real number, as is the forget gate here. Okay, and so what we're doing is we're actually weighting these two vectors, the CT minus 1 and sort of the traditional Bellman network vector. Okay. And so the cell is essentially trading off between those. And the reason that this can combat the vanishing gradient problem is that the forget gate is actually allowing direct information to flow through without any nonlinearity. And so it can essentially pass right through that gate without being squashed by some function like tan h or a sigmoid. Okay, so with these little cells, we can now build up an RNN just as before, where now each of these cells corresponds to the content of this cell. Like what's really going on in this picture is sort of two vectors. One of them is vector C1, and the other is vector H1. And that goes for each of these, where we now have vector C2 and vector H2, and so on down the line. Okay. So information is then flowing through these cells. But so in general, though, you'll see these depicted. We kind of think of them as now, these are just sort of two halves of the same coin. And so pictorially, we tend to draw these LSTMs as though C1 and H1 were just sort of one vector all concatenated together. Okay, so just as we could build up multiple layers of a regular L-man network, we can also build up multiple layers of an LSTM. And so here we just have LSTM units in the individual hidden layers. And what we find is that these tend to be a lot easier to learn in practice. So I have this comment that there's no additional representational power over a deep RNN. So a deep bidirectional RNN. There tend to be these statements that we make about deep neural networks, like a neural network is a universal function approximator, and they tend to be true of a lot of the kinds of models we talk about, so long as you give them enough parameters. So I tend to think these sorts of representational power theorems that we have at the moment are not terribly informative. And so, but what is terribly informative is, in practice, time and again we've seen LSTMs repeatedly outperform L-man networks. Okay, so there's this paper I love that came out in 2015. And what they did was essentially neural architecture search over many different possible cell architectures akin to those found in an LSTM. And what they did was they just basically took the notion of an LSTM cell and said, okay, well, it has some gates and some nonlinear functions, but what if we just searched over the space of sort of possible arrangements of these variables, maybe you have 2 gates, maybe you have 1 gate, maybe you have 5 gates, whether you use sigmoids or tan h's or ReLUs, you could try all these different things out and connect them up in all different ways, and then evaluate each of these cells on a bunch of tasks. And that's exactly what these guys did. And after looking at 10,000 different LSTM-like architectures, they found actually there was a bunch that actually worked just about as well as an LSTM, and sort of exhibited similar properties. And so the GRU is just sort of one example of one that has become popular, partly because it's computationally more efficient. Okay, so when we're using RNNs, one of the things that we tend to rely on is mini-batch stochastic gradient descent. Most of you have probably seen this before. So gradient descent is computing the true gradient exactly from all of your n training examples. Stochastic gradient descent is approximating that true gradient by the gradient of one randomly chosen example. And then mini-batch SGD is approximating the true gradient by the average gradient of k randomly chosen examples. So mathematically, we can think of this as all of these are of the same general form. This is another meta-algorithm, right? So the meta-algorithm is, while not converged, update theta to just be theta minus some step size lambda times g. And the question then for the meta-algorithm is, well, what is g? For gradient descent, g is just the average gradient over all the examples. For SGD, it's the gradient of one example. And for mini-batch SGD, it's the gradient of, say, S training examples randomly chosen. So in practice, the way that this is written, we just said that the mini-batch would maybe be itself randomly sampled every single time. So there's like a different collection of examples every time. In practice, what we often do is we just take our data set and we divide it into mini batches, and we just keep reusing the same set of mini batches over and over again. And this tends to work okay. Okay, so training RNNs can be a little tricky, and so it's worthwhile to have a few tricks up your sleeve. And essentially all of these tricks extend from the fact that when we're building these models, the key component of them is essentially just matrix multiplication. And so one of the most important of these is mini batching with masking. And here, I think, Austin isn't here, but I think you guys are probably going to talk about masking in recitation 1 for the homework. And it's also called padding. And essentially, what I want to highlight is just the notion of the size of the mini batch can have a really dramatic effect on the speed of your RNN. So here, what we're looking at are some results on RNN-LMs, and we'll talk about recurrent neural net language models in just a moment, but they're just sort of a flavor of RNN. And in this table, each column corresponds to a different deep learning toolkit, and the rows correspond to the same model but with different sizes for the mini batch. Okay? So when you have mini batch size 1, let's focus here on DI C++, which is DINET implemented in C++. They also have a Python interface. But in the C++ case, this first column, you get 190 words passing through this RNN-LM per second. If instead you go up to a mini batch of size 64, you get 2,440 words per second passing through. And this is at training time. So one thing to note is that 190 words per second, that's actually pretty bad. Just in general, that sounds really slow. And yet, if you remember back to, for example, the part of speech tagging results that we were looking at for greedy learning to search, those were operating at something like somewhere in the range of 2 to 400,000 tokens per second. And now we're just talking about 3 orders of magnitude slower for training this model. Okay. So here, what we're seeing is that just the mini batch size has a dramatic effect. So another note here is just that sorting into buckets of similar length sequences can help a lot. So imagine if you have a machine translation data set, and some of your sentences are really short, and some of them are really long. What we find is that if you put all of the short ones together in the same mini batch, then the masking and padding trick that we just talked about ensures that you can kind of save a ton of computation time just by keeping all of the short sentences together and keeping kind of all of the long sentences together. And then the last trick is truncated backpropagation through time. And this applies when you have really long sequences. So you could imagine if you were trying to process Wikipedia articles where sometimes the Wikipedia article was actually too large to fit in your GPU memory. So in this case, a common trick is actually to divide your sequences into chunks. And then you can use the final vector of your previous chunk as the initial vector for the next chunk. Okay. So what does this look like? Well, if you have an RNN like so, we can say that essentially it's going to feed along forward until you get your final vector. Okay? But let's say that that's all that fits in memory. So if that's everything that fits in memory, then what we can do is say that the sequence actually continues for another, say, 3 words. And we could just start over from scratch and build a completely distinct RNN here. Or we could take the last vector from the previous chunk and feed it in as the initial vector for this one. Okay. So now you should be asking yourself, how does this solve anything, right? Doesn't this just mean that we're back to a situation where we need to fit the whole thing in memory? And the trick is, well, not really, because we don't actually backpropagate through the second chunk back into the first chunk. Okay? We should, but instead we're just going to pretend that for the purposes of backpropagation, this arrow didn't exist, and so it stops there. Okay? And so this allows us to fit in memory these long sequences that we otherwise couldn't. Now there are further tricks where you can actually backpropagate through this, and it just requires another forward pass through the first chunk. We can talk about that offline if you're interested. Okay, so essentially RNNs form this powerful tool for working with sequence data. And what I want to talk about now is applying them to a particular problem, which is that of language modeling. Okay, and essentially what we're going to be thinking about here is how to take 2 really big ideas and put them together. The first is that of neural embeddings, and the second is recurrent language models. Okay. So the first thing that we need to have in mind here is what it means to actually build a language model. Okay. And essentially you can think of a language model as defining a distribution over sigma star. So here, sigma star is corresponding to a setting where we say let sigma be a vocabulary say, this could be characters or it could be words. And what we want to work with is sigma star. So the question is, what on earth is sigma star? Does anyone know the name of this little star that we're using here? Oh, sure, it's an asterisk. But it has a mathematical name when we use it in this way. Anyone recognize this syntax? Maybe what what's the use in algebra?
So, using the initial set, we try to form combinations of.
Yes. Yeah, so it does make an appearance in algebra. I was thinking of its source as, I think that its use in regular expressions is related to the algebraic notion. So in a regular expression, star has a specific meaning, right? And so specifically, a star here refers to what's called a Kleene star. And it just means that we have 0 or more occurrences of strings in sigma. Okay. So this really is just sort of the most basic regular expression syntax that we can come up with. And what we would say then is that a language model this is a definition of the thing, gives a distribution over sigma star. So what we could say further is that we're going to end up with some probability distribution that is a joint distribution over elements x for all elements x in this set sigma star. So what does this imply about xt? What's its type? So if a vector x is from sigma star, then what is one element in that vector x?
Sigma.
Yeah, it's just an element of sigma. Okay. So what we're doing is we're defining probability distributions, like this one. And if we wanted to, we could actually decompose this using the chain rule. And we could write, if the length of this vector is capital T, then this is going to be the product P of x given xt minus 1 all the way down to x1 times the probability of xt minus 1 given xt minus 2 all the way down to x1. And this product would continue all the way down until we get to something like probability of x2 given x1 times the probability of x1. Okay. This is nothing but the chain rule of probability. And what it allows us to do is sort of decompose a language model into a probability of sort of one word at a time. So already you should be looking at this and thinking to yourself, this seems to harken back to scoring functions that we had been talking about in learning to search. Right? In what way could we use a language model in learning to search?
So, we want to maximize the probability, so we can go term by term and see, given this word, what will be the next probability of, like, probability of x to be the next one, which will be this.
Yeah, so what is so maybe putting the question another way, what would be, if we wanted to use a language model in learning to search, what would these vectors of x's correspond to in the learning to search paradigm?
It would be like a trace throughout the search tree.
Yeah, exactly. It would be a trace or a path through the learning to search tree. right? And maybe you don't actually have the full path all the way up through capital T. Maybe you only have some partial sequence from x up to, say, t minus 1. Well, you could just multiply those lower terms together, and that gives you a score, a probability, for the probability of the part of the sequence that you've seen so far. And so essentially, each of these little probability terms is kind of like one of those scoring function terms, right? It's conditioning on every part of the path that it has seen so far. Okay.
What is capital T here? Is it the size of the dictionary or?
Oh, good question. So here, what I'm using capital T to denote is the length of the sequence. So, number of, say, words in the sequence. Or rather than words, we could even just say tokens.
For a language model, we are predicting a sequence. So do we know the length of the sequence?
So a language model, let's make sure we have our definition straight here. So a language model, what we're defining a language model as is just a model that gives a distribution over sigma star. So for any element of sigma star, it gives a probability to it. So there's a separate question of how will we use a language model? Will we sample from it? Will we use it to score paths through a tree? There's lots of different uses of a language. Maybe do we combine it with some other probability distribution so that we can get improvements in machine translation or acoustic speech recognition? There's lots of different uses of a language model, but we haven't really said how we're using it. We're just saying that it's a model that gives a distribution over sigma star. So that's an important distinction, that what we're talking about here is just the model, not the inference task that we would do with it. Okay. Okay, so now we can look at this little example where what we're seeing here is a bunch of different sort of conditional probabilities from a language model. So what this language model is giving us is the probability of some target word, WT, right, which is one of these, given all of the words that came before it, right, in a 5-word window context. Okay? And so for the same context, the cat sat on the mat, for the same context, the cat sat on there are many different possible targets, like mat, rug, hat, dog, the, sat, robot, printer, right? And what our language model is doing is giving us scores for each of those different possibilities. And so among those possibilities, it gave the highest probability to mat, but it also gave pretty high probability to rug. So if you were trying to build a speech recognition system, a model that can tell you that those are high probability words given the prefix the cat sat on them could actually be really useful. Because maybe your acoustic speech recognition system is working in a noisy environment. And so someone's speaking into their phone and they're saying something like, the cat sat on the mat. Okay. But right at the moment when that critical word came, you couldn't really hear it because there was some background noise, right? And so in that setting, it would be really useful if you knew a lot about the language that is being spoken such that you could make an educated guess about what was likely to come next. The person probably didn't say, the cat sat on the. Maybe they did. Maybe they stuttered because they dropped their bottle. But, the cat sat on the dog, right? Again, this is just sort of a low frequency thing, right? I'm sure there's a YouTube video of that, but it's unlikely. Okay, so one way that people built language models was using n-gram models. And the whole idea here was that you had a fixed window of context. Specifically, n words that came prior to it. And so the trick then is sort of coming up with an actual probability distribution based on some data. And so one way of actually doing that is by looking at, say, the number of times that a particular target word appears. A target word could be cat, or it could be rug, or mat, or something like that. And then the context is going to be whatever came before it. So in this case, what we're looking at are just is a unigram model. A uni meaning one, because we have one word of context. So what we can see then is that we're going to count up the total number of times that in our data set the word chases appears. Okay? And that would be, a sum of all the entries in this column. And to get the probability of cat following chases, we would say, well, let's just take the number of times that cat follows the word chases and divide it by the total number of times that we see the word chases. Okay. So what this allows us to do is then define that language model, which is a joint distribution over any string, in a much more compact form. So we no longer have infinite context. We just have a window of size n for context. And what that would look like, a window of size n minus 1. Here, this is actually a bigram model. So this is a bigram model because we actually are modeling pairs of words, or bigrams. A unigram model would only model one word with 0 words of context. Okay, so this is a trigram model. Okay. And you can see it has n minus 1 or 2 words of context. And so what we can see then is that the joint distribution of W1 up to WT, we can first decompose using the chain rule, but then we say that, the probability of, say, word 6 conditioned on word 5, 4, 3, 2, 1, we're actually going to approximate it by just the probability of word 6 given the 2 previous words. And likewise, we're going to approximate the probability of word 5 followed by the 4 previous words by just, again, the 2 previous ones. Okay? And so when we multiply all of these together, we have the probability of this full joint distribution. Okay. So this is nice too because if you want to store a trigram model, at worst you need a finite number of parameters. How many parameters do you need if your vocabulary is of size V? V cubed, right? So for every triple of words, we need to store 1 parameter, the probability of the third word following the previous 2. Okay, in practice, do we actually need all V cubed parameters for, say, a model of English? No, why not?
You only need ones that actually appear.
Yeah, many sequences of 3 words are just never going to appear anywhere. And so if you're actually building this probability distribution using some data set, many of those trigrams just won't appear. So you only need to store the ones that do. Okay, but this is still inherently limiting because we're restricting ourselves to finite context. Okay. So how could we get back to sort of this chain rule setup where, the probability of that is actually able to look back at all the words that came before it? Okay. And the answer is to use an RNN. So the sort of first key insight here is that we want to be able to represent each individual word as a vector. Okay, so how do we do that? Well, if you've ever built a naive Bayes model or something like it for document classification, you've probably had to think about how do you take words and turn them into vectors. And so what we've done here is just to take each word and represent it as a one-hot vector. Where the vector consists of all zeros except for a single one corresponding to the index of that word, the. Everything else is 0. Okay, so the index of the word cat happens to be all the way up at the top here. And so we have this 1 in the cat position and 0 is elsewhere. Here we have a 1 in the sat position and 0 is elsewhere, and so on down the line. And so when we see the again, it's the same vector as we had in the first time. Okay, so if we take one of these one-hot vectors and multiply it by a matrix, essentially what we're doing is we're picking out one row of that matrix. And so that's what these little v's are, or sorry, u's here. They are little vectors representing the type of each word that's being fed in. And they're going to be much smaller, where the length of those initial one-hot vectors is the size of our vocabulary, so maybe like 10,000 words. The length of these little u vectors, these are maybe only 300 or something like that long. And so the idea then of a language model is that we could use these vector representations of our words as input to an RNN, and what we could get out at the end is a vector. So these little z vectors are connected together by an RNN, and at the end we could get out some representation of the actual context. And finally, if we just define a little distribution over words, say a probability of a word given its context, as a softmax over this final z vector, say z5, then we can recover a probability distribution over our entire vocabulary based on this vector z5 that is an encoding of all of the words that we've seen so far. Okay. So basically, what we could say then is that so here's a picture of this RNN, and we're going to build it up sort of one state at a time. And so you can see that what we have is sort of something that looks just like an Elman network here, right? Where we take zt minus z here is the hidden unit state. And so we're multiplying zt minus 1 by some matrix, and then we're multiplying that one-hot vector wt times some other matrix. Those are going to have the same dimension, and we add them up. And we pass them through some nonlinear function like tan h. Okay. So this gives us the hidden unit at the next time step. Yeah?
Can you just go back once and explain what the C was? So you said
Oh,
it's
sure.
W given C.
Yeah, sorry. So this, the slides notation is using C to denote the context and W the next word. So here, C is really shorthand for W1, W2, W3, W4, and 5. Is that right? And this is really W6. That's what I should have written. So it's a distribution over the next word, W6, conditioned on all the previous ones. Okay. So here, that's actually made a little bit clearer, right? Where we're actually now relying on a recursive definition of how it is that we fold in the context of all the previous words, right? They're folded in via this dependence of zt on both zt minus 1 and wt. Okay? And then the distribution over the next word is given by a softmax taken of a matrix times zt. So what we do then is we start with some input word, w1, and some initial state vector, say z0, and we multiply w1 with u and z0 with w. We add them up, we pass them through that tanh, and that gives us z1. Okay. And we can use that z1 by multiplying it with another matrix B, passing it through a softmax, and the result will be a distribution over the entire vocabulary. So next we feed in word W2. Now we already have Z1 from the previous work that we just did, and that's going to give us Z2 and a distribution again over P of W3. Okay. So we can walk down the line and we get a distribution at every time step.
Will not that be P of W3 given W3? Or will it be the distribution of cat? Will it be just the distribution of cat, or will it be a conditional distribution?
So yeah, it's a conditional distribution. So let's jump back here. So this, again, is really what I was writing before, right? So it's the probability of W3 given W2 and W1. Okay, so always this final distribution is giving us the probability of the word at time t given the word at time t minus 1, the word at t minus 2, all the way down to word 1. So we always have that complete distribution. Okay, so now the question is just how do we actually train this thing? So we want to do sort of the usual empirical risk minimization thing or the maximum likelihood estimation thing. And so we want to say that we're going to maximize the log probability of our data, or the expected log probability under the distribution over word sequences or word vectors W given by our data. Okay. So then the key idea here is that we're going to need something that actually is a target. Right? So if we want to train this vector, okay, so now we've switched from here, these were Z0 and Z1, these are now H's, okay, for our hidden unit vectors. And what we want to do is train in a way that we maximize the likelihood of the true sequence that we observe in our training data set. Okay? And so what we could do is we could say we're going to feed in the word the, and we'll get out a distribution right here, a distribution over our vocabulary. And so during training, we're going to choose to maximize the likelihood of the next word that's about to come. And then we do the same thing. Now we feed in the next word, and we get another distribution over the vocabulary. And then we train to maximize the likelihood of the third word. And so on down the line. So every time we're training these hidden units so that they take on values that are good at predicting the next word that's to come. Again, we kind of raise this question of, why are we going left to right? Well, you could go right to left just as well. Maybe it depends on the language that you're actually working with. Okay, so now suppose you actually wanted to sample, oh, question.
If you're training just on the next word,
Mhm.
then how is it like carrying through? Or like how is like the first word affecting the rest?
Oh, sure. So in this picture, the distribution, we could think of, so here I was kind of drawing in these little pictures of probability distributions. And the question is, in practice, what are these distributions? So if we look at these words as W1, W2, W3, W4, and W5, this distribution is giving us the probability of W6 conditioned on W5 all the way down to W1. Okay, so how does it get the dependence on all of those words? Well, it depends on them through these hidden vectors. Okay, so this previous distribution is really just the probability of word 5, the, given word 4 all the way down to word 1. And so on all the way back until we get to the probability of word 2 given word 1. Okay? And so if we multiply these 5 probabilities together plus some prior probability of the word 1, then we get back a joint distribution over all of them. Okay. So we can draw samples from an RNN-LM, and here is where you get a performance of Shakespeare. So I'm actually going to read you a segment from As You Like It. So why Salisbury must find his flesh and thought that which I am not apt, not a man in fire, to show the reigning of the raven and the wars to grace my hand reproach within, and not a fair our hand that Caesar, wait a second, this reads kind of weird. Huh. Is that the As You Like It, or is it that way? Shoot, I have both slides in here. I don't know, actually. So wait, which is the real Shakespeare here? Okay, so if you look carefully, the thing on the left, it actually has like some weird things going on in there that I'm pretty confident Shakespeare would not have written. But it comes across sounding rather Shakespeare-like. Whereas on the right, we actually have the real As You Like It, Charles and Touchstone, and they also sound, in usual Shakespeare form, a little bit incomprehensible. But what we're looking at here is actually the output of an RNN-LM that was trained on Shakespeare characters. So here, sigma was defined to be the set A, B, all the way up through Z, plus some punctuation. Okay. And so it's not even modeling full words. It doesn't even know what a word is. Because in addition to these, we also need things like a space, which is in our vocabulary, and a period and a comma, right? These are all elements of sigma. And so sigma star is then all possible strings. And you can see that the RNN-LM, when trained on Shakespeare, is able to realize that in general, we like to start Shakespeare with all caps names of people who appear in the play and follow those by a colon. So it figured out that structure of the actual Shakespeare. And then it also figured out how to produce things that look really like words, and also some things that maybe are not actually words at all, like APS. But, it was plausible. I was able to pronounce it. Okay. So the RNN-LM is able to do an incredible job modeling data in this way. And if you look at essentially perplexity, which is sort of the standard metric for evaluating language models, what you'll find is that over time, the state-of-the-art models have essentially been dominated by deep recurrent models. Okay, so at present, the sort of state of the art as of today is a model called GPT-2, which is technically is a transformer network. But if you kind of trace back the origins of this network, you'd find that it would kind of lead you back to the earlier recurrent neural network language models that were introduced in, say, 2003. And so these have come now to kind of dominate the space and are used all throughout sort of real-world applications of language modeling. So things like,
In the previous slide, when you generated Shakespearean text,
Yep.
how did the generation happen? Did you first sample a single character and then following that you sampled the rest until when?
Yeah, so this is a great question. So how would we sample from a language model? Okay, so one way that you could actually think about it is to think of the language model as defining a policy. Okay, so at every step along the way, it's going to condition on all the words it's seen so far, and then choose a next action. Okay. So the next action is the next character that it's going to generate, say one of 26 characters, say 36, it's probably more with punctuation. And so among those 36 characters, we're going to randomly pick, according to the probability distribution, over those next characters. And then we'll feed that back into the language model as sort of our next output, and then repeat again. So it's just like stochastically following a scoring function through a learning to search tree. Okay, so that connection is so strong that I actually want to take a moment to look at what it would look like to actually use an RNN-LM to score a path through a tree here. Okay. Oops. Lost that device. So, okay, so if we want to think about an RNN-LM, then it's useful to see how to score a path in a search space. Okay. And so what we could think about here is that what we care about is something like our part of speech tagging example, where we have some start state, and then we have neighboring states like noun and verb. And from verb, let's suppose that we pick verb. We can choose among preposition, noun, or verb. And then from preposition, we can choose determiner. And then from determiner, we could choose noun or verb. Okay, and let's suppose that the path that we're interested in is this one. So the picture that we want to have in mind here is how an RNN-LM could actually score that particular path. So we could say that the RNN-LM is going to have some initial vector, and we're going to feed in some token like start, okay, at the first time step. And then we'll get out some distribution over our vocabulary of, in this case, part of speech tags. Okay? So we could actually show this complete distribution because in this case, we're only talking about nouns and verbs. So there's some probability of noun and some probability of verb. Okay? And at this point, we can actually proceed along where we're going to feed in verb. Okay. And we'll get another probability distribution, this time over 3 options, preposition, noun, and verb. And so each of those have some probability. And we'll just continue on along our way, this time feeding in a preposition and getting a distribution. In this case, it's kind of completely uninteresting. It's just a distribution over determiner, okay, because our search space has kind of been restricted. And then we'll feed in determiner to get a distribution over noun and verb again. And finally, we'll feed in our selection of noun to get a distribution, say, over something like an end token, and also, noun and verb, which would allow us to continue along. So what we're looking at here is if we wanted to do prediction, right? For each of these probability distributions, we would take an argmax. Okay. And if we took an argmax, then maybe in this case we would get lucky and we would say, okay, V is the correct thing, so it's going to be fed in back here. Okay, and then we take another argmax over this distribution, and we get lucky again. We get the P, and so P is going to be fed in here. And then here, there's really just one option, so the argmax has to return D. Okay, and then here, the argmax didn't actually return the correct thing, noun. It actually returned some other thing, like verb. Okay. Okay. So now, if we were predicting, we might actually end up feeding in verb here instead of noun. Okay? And that would actually correspond to the score for a different path. Okay? And then finally, we get some end token here. And that tells us to stop. Okay? So this is nice. It shows us how to do prediction. But we could also look at how to use this network if we wanted to train the network. Okay. So if we were concerned with training, then we could build up a little bit more of the computation graph, and we would find that we have our goal sequence, right? We know what the true sequence of tokens was. That's like our Y star. Okay, and it consisted, say, for our sentence is something like flies like a plant, I think was our running example here. Okay, and so the true sequence is actually noun, verb, determiner, noun. Okay. And so what we could do then is we could construct a cross entropy for each time step by feeding in the true prediction and the probability distribution over the vocabulary. Okay. And then likewise, if we wanted the probability or the log probability of verb here, we would just need, again, that distribution and the correct one to pick out the corresponding probability. Okay, and so again, we'd feed these in all the way down the line, and I guess all the way including an end token here. And at last, we could then take all of these little cross entropy terms and add them up, and the result could be the value for our loss function. So once we have that loss term, now we have a computation graph, and we can just back propagate through it. Okay. So at this point, we could also raise the question of how do we actually sample from a language model? And if we wanted to do that, well, we could just have another procedure in here, which is sampling. And sampling, just instead of doing argmax, does sample. And it just takes this distribution and it gives us one of the possible outcomes. Maybe we randomly pick an n, and then we feed that n back in down here. And then we randomly pick, say, another n, and then we feed that back in down there, and so on down the line. So mechanically, it looks kind of like following a greedy policy, except that instead of taking an argmax, we're taking a sample at every step. Okay, so I guess the remaining question here is, what about the sentence? Okay. Well, unfortunately, it's currently ignored. So that's not good, because what we want is a model that actually takes the sentence into account. Okay. So the key idea here would be maybe we could encode it as a vector and then feed it in right here. Right now, the model only looks at the tag sequence, but if it had an initial vector that knew all about the sentence, that summarized the sentence, then maybe we could actually condition on that whole sentence. Okay, so this leads us to the notion of sequence-to-sequence models. And the motivating question there is, how can we model the input-output pairs when the length of the input might be different from the length of the output? And so to do that, what we rely on is this notion of an encoder-decoder architecture. And an encoder-decoder architecture, or a model, it's used all over the place. I mean, for acoustic speech recognition, or machine translation, or image captioning. And in all these cases, the architecture kind of looks the same. You have some input that is fed into your encoder. And what comes out at the end is some vector that represents the input. Okay. And then you feed that vector into a decoder architecture that spits out your output. Okay, so if we're doing speech recognition, then the input is speech, and the output is a transcript. If we're doing machine translation, the input is, say, your source language, like maybe English, and your output is your target language, like maybe Spanish. And then if you're doing image captioning, well, then you can feed in as input your image, and your output could be the actual caption for that image. Okay. So, okay. Oops. So how could we actually build one of these things? Well, what we could do is we could say that we could build up some architecture that just puts together, say, two ingredients, a by LSTM and a recurrent neural net language model. And so the model that would result, say we were doing something like machine translation, would take as input our X, like how are you, and it could feed in those word vector representations, and then it could send them through a bidirectional LSTM. Okay. Okay. And what it could then do, let's actually make that a little more precise. Okay. So here the inputs also feed into this second layer. And then we can have some vector, let's call it Z0, that represents the entire input. And it does that by taking the last vector of the forward LSTM and the first, or last, however you want to read it, vector of the backward LSTM. And then, here's the fun part, it feeds it into a recurrent neural net language model. And so, now we can just do as before. We feed in a start symbol, and we get out a distribution over our vocabulary. Okay. And then we feed in, and say out comes, if we take an argmax, some translation, and we feed that back in and get another distribution over the next word, which might come out as como. And como is fed back in to get another distribution over the vocabulary, from which we predict estás. And finally, we get our last distribution, which yields our last question mark. Okay. And so what we're left with here is the by LSTM encoder and an RNN-LM decoder. Okay. And the sort of key remaining question is, how do you actually train this thing? Well, essentially all you're going to do is you need to build up a loss function for the RNN-LM. Okay. So what does that look like? Well, it looks just like what we did here. So there's one last detail that I have to leave you with, so I'm going to run 2 more minutes over. So there's two training algorithms that you should know. One is called teacher forcing, and teacher forcing is really just the neural net deep learning way of saying supervised approach to imitation learning. Okay? And so the approach on recurrent neural nets is you feed the ground truth from the previous time step in as the input to the next time step. And then at each time step, you're minimizing the cross entropy of the ground truth. And scheduled sampling is the deep learning way of saying online dagger. So what you do is you feed the model's prediction, or with some probability, the actual ground truth from the previous time step in as the input to the next time step. And then at each time step, you minimize the cross entropy of the ground truth for that time step. And the last detail here is that you gradually decrease the probability of feeding the ground truth with each iteration of training. This is the beta schedule that we saw for Dagger last time. And so if you look at scheduled sampling, what you'll find is the reason that it's called scheduled sampling is that you can have different schedules, like the ones that we talked about for different sequence of beta values, trading off which mean the mixture of the oracle policy and the model policy. And you can see the red line is showing the exponential decay that we showed. If you use that, it gets you back exactly an instance of dagger. Okay, these other ones, inverse sigmoid, linear decay, well then you need to double check that they actually satisfy whatever other schedule you're using. You need to make sure that it actually satisfies the dagger requirement that the average sum is decreasing to 0. Okay? And if it does, you get the theoretical guarantee. If it doesn't, you don't get the theoretical guarantee, but as you'll do on your homework, you can actually evaluate whether it still works out okay in practice. And it might. Okay. So when we pick up next week, I'll talk about some actual examples of seek-to-seek for machine translation, acoustic speech recognition, and image captioning. And we'll say a little bit more about sort of some of the fun details that make these things work well. Okay. So thanks for staying a couple minutes late. We'll see you guys next week.